This is IAT355, lecture 9.4, continuing on our conversation about trees. In particular, this is part 2 of space filling or enclosure as a means to depict something, to depict both structure and quantitative values in tree structures. So just recalling from lecture 9.3, this is the kind of visualization that we're talking about. So this is a tree of all the cars sold in the US in 2017. The top of the hierarchy is all cars. The next layer in the hierarchy, the child nodes of that hierarchy, first layer down below the root is the brands, car brands. So here's Ford here, Toyota, Chevrolet, Honda, Nissan, Dodge, etc. And what's going on to identify what the brands are, of course, the brand logo is drawn as a kind of a background wash and a distinct color for each brand, although they're using a lot of blue in this one, so it might be a little bit harder than it would otherwise be. Of course, with below each car brand is an individual model. So here's the Ford F-Series, there's the Ford Escape, etc. It's a shallow hierarchy, and it's pretty good for a good use case for tree maps. So you'll recall from just having looked at that example that one of the problems with the original tree map algorithm is that it tends to develop long, thin aspect ratios of rectangles, and that arises because of the original algorithm starting by taking a bunch of vertical slices, then horizontal slices. Doesn't matter which way what place you start, and it could be that cutting up the space according to a small number of slices results in some of those slices being very long, and then slices within that being very narrow, and that's due to the variable number of slices per layer. And the strict algorithm of going horizontal first, then vertical first, then horizontal first tends to result in these long, thin rectangles. However, it's a good representation of beyond what node link diagrams can give you. You can use color to represent something important, typically a category, car brands in the previous one, as well as area, which is depicting the quantitative value that you care about, which is the number of vehicles sold. So long, thin aspect ratios tend to be a little bit hard to understand and hard to use. In particular, understanding their area gets to be a little bit problematic. So here's a quiz question, an off-the-cuff quiz question. Which one of these two light blue rectangles is bigger? And the answer is they're both the same size. And it's a little hard to tell that just by looking. You might be able to kind of think about it, but that's kind of not really what you want to do. You want to be able to sort of look at it and say, oh yeah, those things are the same size. And because area is the thing that is used to depict the quantitative values, so you want to kind of have all the rectangles be roughly the same shape if you can manage it. Bigger or smaller, and small variation in shape. So how do you get more squareness, or things being as close to square as possible? Can you force a rectangle to be more square? Well, if you were to do so, what you would end up doing is probably doing something with all its neighboring rectangles. Kind of left off the table is the idea of changing the shape of things to be some complex polygon that fills up the leftover space or something like that. That would be hard to understand because you wouldn't understand what the area of those shapes. So you kind of want everything to continue to be squares. So when you change one shape, you have to do something with the other shapes, and you have to do it in 2D, not just 1D. And this turns out to be a very hard problem computationally to do exactly. So what the algorithms that you'll see as we move forward, and indeed in the car example, what they do is they fake it somehow. They come to a close enough approximation, and that results in good enough displays, and we'll show some examples of that. So let me just talk about NP-hard. I told you on the previous slide that making rectangles more square is NP-hard. What is that? And so I'll just take a little brief side trip here. One of the things that's of interest to computer scientists is to measure how long to compute a solution to a problem. And to estimate that solution time on the basis of how big the problem is just simply the amount of stuff that's in the problem, the amount of data to process. So the size of a problem, for example, sorting, a list of numbers or sorting a table in Excel or something like that, that depends on the number of elements in the table. Typically you would sort on, one column or something like that, and the more table elements there are, the longer it takes. Surprise, surprise, right? There are some algorithms that take 0 time, a few of them, and there are some things that take linear time. That is to say, the more items pretty much is a linear function. The amount of drawing time, for example, for drawing polygons is roughly equal to the number of polygons times some factor. Sorting, as I just finished talking about, is typically at its best n times the logarithm of n, mainly because you can come up with sorting algorithms that take advantage of local coherence. Quicksort's an example of an n log n sorting algorithm. However, there's a broad class of algorithms, which I'm just labeling here as optimizing, find the best configuration. And those are optimizing in situations where the first choice you make affects all the other choices that you have possibly left to make. So you choose for the first move to make, then the second, then the third. That will give you likely a very different solution than choosing the third item I mentioned, then the first, then the second, which will get different again from choosing the second, then this third, and then the first. And the reason why is that in optimizing algorithms, the first choice affects everything else. And so therefore, if you want the best solution, you have to try all configurations, which means all orders of selecting the items to put first, then second, then third. And that takes, as this equation intends to indicate, an exponential amount of time. That's c to the exponent n. That is to say, n is the exponent, some constant times an exponent, and that's a crazy amount of time. So you can't really solve those problems exactly, but you can fake it. So an example of us human beings solving that problem for real is, for example, when you move house. You fill up a moving van. Let's say you're doing it as opposed to a moving company. You fill up a van with stuff. Well, you don't just take the random stuff and just the order it comes out of the house and shove it in the moving van. That'll never work. You'll waste a lot of space. What you do instead is you put the biggest things in first. The mattresses, the box spring, the couch, the big stuff first. And the reason why is the big stuff, where you put it, affects where you can put all the rest of it. So the kind of the idea we all have in our minds, if you put the big stuff in first, then you can put all the smaller things around it. Whereas if you put smaller stuff in it, you can't put big things around it. So that's kind of a natural sort of intuition we have about filling moving vans. And the same thing is what's going on in these squarifying algorithms that we're going to now go back to. So I just am reminding you, if you're moving, put the big stuff in first. So the cluster tree map, or the variations on the squarified tree maps that I'm about to show you, are behind the scenes running an algorithm that allocates space, starting from the biggest things going down to the smallest things. And every now and then, when they do an allocation, what happens is, the stuff that they're tree mapping, unless it's just, a fixed data set, might come up with different answers on the basis of what is biggest, say, this week. And so an example of that I'm going to show a few screenshots of is this thing called the FinViz map of the market. FinViz means financial visualization. And what it does is it illustrates stock movements, and it uses color for that. And it compromises the tree map algorithm to avoid bad aspect ratios. That is, long, thin rectangles. Instead, most of the rectangles, are at most 4:3 or 5:3 aspect ratio at its most oblong. And it's got doing the basic divide and conquer algorithm, probably with some hand tweaking behind the scenes. If they got a bunch of solutions that are automatically computed, they pick the one that's most like the previous solution and is most visually appealing. And it takes advantage of the shallow hierarchy, and so we'll show what that means in a minute. So this used to be called the Marketwatch map of the market, and then somebody bought a company, blah blah blah, and so this is the Marketwatch map of the market. from February 2013. And what it's doing is showing all of the stocks in some aspect of the stock market. I think this is probably the broader stock market in the US. And so we have up here these labels for sectors of the stock market. So that's healthcare, financials, oil and gas, utilities, basic goods, industrial stocks, telecom, consumer services, technology, consumer goods. Keep your eye on technology. So you might guess what the big ones are. This one's, I think, Microsoft. That one's Apple. And the color indicates whether the stock price is rising or falling. And the size of the rectangle is market capitalization. And what that is the total number of shares multiplied by the share price. So if the price is going up and up and up, a rectangle will grow. If the price is decreasing, 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 these rectangles over time will shrink for an individual company. And you get a fixed amount of area and it just draws the entire stock market. So it's giving a sense of the relative increase or decrease of values in the large by the basis of the size, and in the small, in the short term, by the color. Red meaning declining, green meaning increasing in this instance. Here is a later screenshot of the same thing. This is the FinViz version of it. It's the same data, the same suite of algorithms, but the labelling is a little different. Technology has ended up moving to the upper left, and the other thing that's happened is that they've indicated there's more space on this one, and they've indicated some subset of, say, the technology sector. What is technology? Well, they mean electronics technology. So here's internet companies. There's Google, Facebook. This is business software. There's Microsoft there. Telecom. There's Verizon and T-Mobile. Diversified. There's a bunch of things. So here's financial. This is all the banks, financial, et cetera, et cetera. Consumer goods. There's Apple here. Here's Walmart. This is in services. That's discount retailers, catalogs. There's Amazon. Basic materials. And this is Exxon Mobil. That's big oil, in case you wondered. That's Total Petroleum here, etc. So not all of these are U.S. companies. Some of them are international companies that have a listing on the New York Stock Exchange and related things. Here's industrial goods, utilities, etc. So one of the things that you probably have noticed is that it's a little hard to compare, because you have to kind of remember what I showed in the previous slide, that some of the sectors have grown while others, relatively speaking, have shrunk. But the most telling thing is coming up on the next slide. I took this screenshot earlier in the week, and you'll notice that there's 5 big stocks: Microsoft, Apple, Google, Facebook, Amazon, and a bunch of smaller companies. Now, they're still gigantic companies. Sorry, I should have included also Alibaba. These are big companies, but what's happened is that the internet companies, the computer technology companies, have grown so large that they're totally dominating the display. Down here, by the way, this is Visa, MasterCard. They've, increased in value. So if you go back, Google was this size. There's Microsoft. There's Facebook. There's Amazon. Sorry. There's Amazon, and there's Apple. And what's happened is that Microsoft has gotten gigantic. Apple, Google, Facebook, Amazon, and now Alibaba. Now, it's not necessarily that Alibaba suddenly burst onto the scene. There's possibly also the factor that, Alibaba got bigger, but also what happened is that it got listed and detectable, so to speak, on this display. Yeah, so it got super big. Anyway, this is all the companies. The other thing that you'll notice is some of these companies are operating in a market segment which, you might think of as reasonably healthy. There's, smaller and smaller and smaller things going off to the right. And that's the outcome of this algorithm of, among other things, cutting horizontal first to have a significant fraction of the area, allocating as many as possible as makes sense. In this case, it's just the one, Microsoft up here. And then take a vertical slice, allocate the next largest to that, and then if it makes sense, take a horizontal slice, but in this case it didn't make sense, so it's just allocating the big ones here. But what you see as an outcome of that is that the smaller stuff ends up in the bottom right of its sector. Okay, so I could continue with that. So here is a live screenshot of this. I wanted to show you the interactive stuff. So here's Amazon, Alibaba again. The other thing I wanted to point out is that you can see, you know, its stock price, which is gigantic, it's increasing in value, etc. But you can also see over to the right, this drop-down menu, all the other stocks in that particular sector. And so that really adds to the impact. I think one of the things you can do with this, you know, you can't further interact with this in an easy way, but it does certainly enable you to inquire more deeply as to what's going on in a particular market sector, and that can be pretty valuable. So the thing looks a little different today, mainly because, you know, at the moment I'm doing this, you know, it's just a different time of day, and the stock prices, some more stocks are increasing instead of decreasing. It was a down day when I took that screenshot. So going back to the slides, we can see that, you know, one of the things that's a real advantage of this thing is that those dynamic interface operations really add impact. In particular, they give you a lot more detail. In the earlier variations of this thing, it would just tell you a pop-up of the individual price of the stock itself and allow you to drill down on that. I think what's happened is that over the last number of years, they've kind of watched at the back end as to what it is that people are really doing with the market map, and really their the kind of focus has been less about browsing in order to investigate an individual company, but to see how the market sector is doing. So they've shifted their focus in the FinViz version of that. There's also a mild zoom ability, and we'll show that in a sec. So as I said, there's a zoom ability, and I'm just rotating the mouse here, clicking to drag it, and I can zoom in further to see. And what happens, of course, is you see, you know, some semantic zooming happening here. You see a little bit more information. As the space gets too small, it hides the stock ticker label. As you get closer, you get the stock name, and as you get even closer, if there's enough space, it gives you the number as to the percentage increase on the day. So that concludes the things I was going to say about the map of the market. It has this moderate zoom ability that I showed you, and the tooltips give you a lot of detail. However, one of the things that tends to happen, as with any optimization algorithm, you can come up with a bunch of solutions. Sorry, the optimization algorithm, you could get a solution, you like it, you stick with it. Next day, next week, you know, not much changes in the stock market. If you decided I need to run the, you know, layout algorithm again, you get a solution that's pretty similar. But over time, as things evolve, let's say Google keeps getting bigger and bigger and bigger, what happens is that it ends up occupying so much space that it starts to push other things out of the way in some sense. And it turns out that in the act of pushing that away, it leaves blank space or does something doesn't work visually. And so what has to happen is a thing that has relatively shrunk needs to move somewhere else so that other things can take the space that will be vacated by that now somewhat smaller thing. And that has happened actually in the map of the market between 2017 and 2020. And that is healthcare moved from its former location to its current location. If you'd like to see, you can just go back in the slides. You know, the indexing thing at the bottom of the YouTube video will tell you where they are. And you can just go back and forth and see that it's moved things around. So, and that's just, you know, the way life is, given that everything, all the prices all the time are always changing. Eventually the changes, the accumulation of all the changes will get to be big enough that it'll cause a different layout. So the thing that tree maps are not necessarily good at is showing structure. So a regular borderless tree map, which is not like what we've been showing here, those things have borders. A borderless tree map makes it challenging to discern structure of the hierarchy, particularly large hierarchies and deep hierarchies. So one of the things that people have investigated doing is changing the rectangles, you know, sticking mostly with that geometry, but trying other visual forms to help supplement our visual understanding of what's going on in the display. So this thing here is something called a cushion tree map. What's going on is you can think of this as a filter that has been placed over top at the top level, where in the center it's kind of the standard brightness, and it gets darker towards the corners. And you can see that very clearly on the right. So there's a shallow hierarchy here, and this is, you know, the first, second, third, fourth, whatever it is, children here. And within that, there's a number of grandchildren. Same with this, same with this. And down here, there's a long, thin, wide node that is the child of parent nodes. You can see more of that structure here. Again, we have long, thin shapes. And you know, the highlight in the middle is where it's at its brightest, and at the corners is where it's at its darkest. So here, 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 and here. And the purpose of this thing is to get across the notion that there's a hierarchy going on, because that's applied recursively as you get deeper and deeper in the hierarchy. You know, the filter rectangle is smaller, but it's doing the same thing. The changes that it's making to luminance are likely to be pretty small, but the accumulation of those darkening moves kind of adds up and makes it comparatively easier to see the structure. The other thing that's funny about doing this is that the thing works best if you don't examine it too closely. If you really, you know, get closer and try to examine it, what's going on is that this cushioning thing is kind of a low frequency signal. That is to say, it varies slowly across the extent of a rectangle. And those things are best picked up you know, when the features are not very small. If you try to magnify them, they get to be hard to see, and that's a kind of a perceptual effect. We haven't talked about that kind of perceptual effect in the perception section of the course, but it's a perceptual effect that's being taken advantage of here. So if you're wondering, this thing seems to work at first and then it seems to fade away, it's because of that something interesting is going on with your perception. So this thing that does this cushion tree map is something called SequoiaView. I won't demonstrate it. It's, you know, there's an old executable you can go get from TUE in the Netherlands. That is a visualization, and this is, you know, yet another file system viewer. But it kind of gets across reasonably clearly what the hierarchy looks like. It gets, you can think of it as either substituting for boundaries that mark, you know, levels of the hierarchy, or replacing those markings depending on how important you as the user select, you know, the labels of where you are in the hierarchy. Presumably also the thing that would really be valuable here is if you have interactive tooltips telling you the path name or whatever it is that needs to be shown for this visualization. One of the other things that can be useful for this is, you know, we've seen how, you know, this primary quantitative thing can be done in the stock market visualization. Plenty of companies have been using tree maps for quantitative visualizations. This one's from Panopticon. They used to have screenshots of this online, but you know, they've kind of buried it in their financial visualization software suite. But one of the things, you know, that thing said portfolio visualization, that's kind of getting at another issue. Clearly, the concept of a tree map is bigger values mean bigger rectangles. And so therefore, logically, if the value is 0, the rectangle size is 0. Perfectly sensible, but there's a drawback. What happens if 0 is actually important? So what I'm going to do now is show a video after talking about it for a sec, where what you're doing in looking at the tree map is trying to understand how to make decisions of, say, allocation. And so, for example, stock or mutual fund portfolios, funds you do not currently hold have 0 value in your portfolio. And if you were to tree map those funds, they would occupy 0 space and nothing would be drawn. So what you do want is for them to be drawn so that you could potentially buy them, or at least on electronically or on paper, propose the idea of buying them and allocating some money to those funds, so you can get a sense of how your portfolio will be balanced. So the task here is a little bit different from the task of finding out what is there, but it's being used as a decision aid to figure out you know, where to spend your money or how to allocate your money. So this FundExplorer thing that I'm about to show shows mutual fund portfolios, including funds not currently held, and the area maps to your relative investment of the fund with a minimum area, meaning 0, except so instead of 0 pixels, it's like 10 pixels by 10 pixels. And you want to help the user of this thing with portfolio diversification. If I had fund X, how much does that overlap with my current fund holdings? So diversification is a tried and true financial investment strategy. If something goes bad in the oil business, you don't want to go broke because all your stocks are in the oil company, in the oil patch. You want to spread your money around so that something going wrong in some sector of the economy doesn't destroy all your investments. So what I'm going to show is this thing called a context tree map. It's a tree map with a small distortion to give 0 valued items altogether some constant proportion of screen area, and provide dynamic query capabilities to enhance exploration, leading to
This video illustrates the FundExplorer system that introduces the concept of a context tree map. FundExplorer helps investors manage their portfolio by seeing fund overlaps and exploring how to diversify their portfolio better. The FundExplorer interface shows the stock market view on the right. Each small rectangle is a particular stock, and the stocks are grouped into larger rectangles that correspond to market sectors. The left fund list area has regions for all mutual funds, filtering operations, and the actual investment portfolio. Let's suppose that we have $1,000 invested in the Fidelity Spartan Fund. We select that fund from the list, put $1,000 into its holding, and give it a light green color. Finally, we add it to our held list. Note how the rectangles corresponding to stocks held by this fund have grown. Their areas now correspond to the relative holding weight of each stock by the fund. In a normal tree map, stocks not held by the fund have a 0 value, so their rectangles would have 0 size and not appear in the display. In the context tree map, however, 0 valued items are given some constant proportion of the display area, and thus each appears as a small rectangle. Here, these items represent stocks not currently held, but ones that could be purchased to diversify a portfolio. Notice here that the Fidelity Spartan Fund does not hold any stocks in the industrial sector. We would like to broaden our portfolio and include funds that hold stocks there. FundExplorer provides an easy way to explore this possibility. By clicking on the border of the industrial sector, it becomes highlighted in red and is used as a filter. Thus, only funds that hold stocks in this sector are shown in the center list on the left. By clicking on a fund there, such as Pegasus International, all the stocks held by that fund are highlighted in a blue outline. Pegasus only has one industrial stock, and it has a lot of overlap with the Fidelity Fund we already hold, so let's look for another option. Let's try out Harbor International, and we notice it has much less overlap, so let's buy $1,000 of that fund as well, give that fund a yellow color, and add it to our held list. Now note how the portfolio view on the right shows our stocks from both funds. When we click on an individual stock such as Nintendo, the filter list updates to only show funds that hold that stock. Clicking on a second stock such as Autogrill further refines the list to only show funds holding both stocks. Acorn International is the only fund to do so here. Let's see how well that fund would mesh with our portfolio. To do this, we simply click on the fund to the left, and all the stocks it holds are shown on the right. This fund appears to be a good fit for us, as it only has a few overlaps with our existing portfolio. Stocks held in multiple funds are indicated here by rectangles that have multiple colors. The size of each region is determined by the relative holding from each fund. We also like Acorn International as a choice because it adds a few more stocks than the technology sector that we wanted to beef up. Notice how the use of repeated item selections and filtering operations provides a kind of dynamic querying capability to the FundExplorer interface, therefore promoting exploration of possible stock and fund purchasing strategies. Together with the context tree map visualization technique, these operations make FundExplorer a potentially valuable tool to investors. Furthermore, these ideas could be adapted to other domains in which exploration and the potential addition of zero-valued items frequently occur.
Okay, so that was FundExplorer. And so the basic idea there, once again, is to show, non-zero size rectangles so you can pick them. And of course, this is driven by the idea of, you need something to be able to select. And of course, visual selection is what we're doing all the time. If you had a good idea of what the names of everything were, probably this technique wouldn't be so strongly necessary. But for this one, clearly, there's so many choices, and it's unlikely that anybody has remembered all those choices. So presenting those choices visually is what you have to do. Another thing to think about is what we've been talking about so far is filling space with rectangles. Some folks have been exploring the idea of filling space with other shapes, in particular radial space filling. So what if we used radial rather than a rectangular space filling technique? We saw node link trees with a root in the center and growing outwards. The hyperbolic tree was an example of that. How about making a pie chart and then subdividing the pie sectors to indicate subtrees and subtrees? And the radial angle will be, and in some ways the area will be indicating the size of the variable, the quantitative value of the area. So let's just see what that might look like. This is another thing by John Stasko. This is something called the SunBurst visualization, and at the center, this is another file system visualization. At the center is the root of the file system, or the home directory or something. Here are 3 subdirectories, a number of subdirectories, and once again color is being used to indicate size. And we can see actually what the colors are corresponding to in this table over here on the left, indicating the file extension for the file type. And so you can see all the purple ones are image files, and there's a few of those. Obviously, there's no video files on here, as far as I can tell. He has a lot of word processing files, but you don't see much of that simply because those files end up being pretty small, much smaller than images and significantly smaller than videos. So the way that thing works is the root directory is at the center, and each successive level is drawn further out from the center. And the sweep angle corresponds to size. Now, this relies a little bit on our ability to detect angle, which is okay. But it's not at the top of our ability to perceive. And color maps to type or to perhaps age, although we just showed type in this instance. And interactive controls allow you to move deeper and out of the hierarchy. So this thing isn't just a still interaction, or wasn't a still interaction, but you double click to interact. But the drawback of this thing is that in large file hierarchies, files at the periphery are usually very tiny and hard to distinguish, and also hard to pick. So another thing, this is a project I was worked on while I was at Georgia Tech. This is something called Zoomology. Basically, this thing started off as being a zoomable browser for the tree of life. It started off for visualizing the hierarchy of bacteria, and this is actually a screenshot that shows bacteria. And what this thing ended up doing, we ended up working on this to transform this into doing tree comparison. Again, incidentally, using the tree of life as the example data set in one of these contest visualization contest things. And some students of mine did well in that contest by showing this tree comparison. So on the left is an example of the tree. On the right is another part of that tree, and at the bottom is a tree diagram. This is also called a dendrite diagram because things hang down from the top. And it's subdividing the totality of the tree of life into subparts, subparts, all the way down. The white area indicates that this part of the tree only exists in one of the diagrams, the one on the left. The one on the right doesn't have that, and that's also indicated here. The stuff in the right here is somewhat less populated. Color is also used from top to bottom to indicate layer or level of the tree. The way this thing works, so you're looking at a still picture and you're wondering, how do you use this thing? What happens is it starts off with a circle with a bunch of subcircles, and what you do is you rapidly zoom in to the part of the tree that you're interested in. And as you zoom in, the stuff that goes out of the view, essentially, you don't see anymore, and it's no longer made to be visible. And the stuff in the center grows and grows and grows. And as you get closer and enough area becomes available to allocate child or grandchild or great-grandchild nodes, you then populate the circle at the time that it gets to be large enough. Typically, you can see that showing here, that in this node, there's what looks like two blobs, right? And so those are two child nodes. If you were to hold the mouse button and press the right key, you would zoom into that. That would get bigger and bigger. And as the two child nodes got bigger, as soon as there was enough space, more than 2 by 2 pixels or something, there would be an allocation process which would allocate room for the child nodes of those two nodes to pop in. So it's highly interactive, highly zoomable, and part of the reason for that is that it's a fixed database, and also there is a hierarchical structure for doing the layout and storing your layout decisions. So all the layout decisions are done kind of in a pre-processing stage, and so you can super fast zoom in and out of this. And this is an outgrowth of a project I also worked on that was about zooming in and out of geography, a la what Google Maps and Google Earth does. So it used the same concepts, not the same data structures, but the same concepts for this thing. And so it's pretty effective at rapidly zooming to the target. In this case, you had to do a lot of reading so that you know where to go, and you had to know something about the organization of the tree of life to be able to navigate it, but it was very good for rapidly examining parts of the tree. You could also, coordinate structures. So this is an example where, the same color, but this thing has two nodes, and this thing's got a whole bunch, and these two, Godzilla's eyes, doesn't exist over here. And this thing has a whole lot of extra stuff that this one on the left does, and that indicates that there's a difference between those two trees. And so that was one of the things that this thing was really constructed for. We had initially constructed the thing to do zooming, and then we did this second piece where it would compare two trees and zoom rapidly, so you could see the same structure in both trees if indeed the structure was similar enough. If trees were completely different, the comparison thing wouldn't be worth doing, but this thing is built for showing, significant but localized difference from one tree to another. So that allows for a comparison of a pair of trees, and, as I said, shows how the tree on the left has less stuff than the tree on the right. So that wraps up, finally, space-filling representation. It's good for trees with a size attribute and a shallow hierarchy. It also makes sense if to do zooming if you have a deep hierarchy, but if you do a lot of zooming, you run the risk of being, kind of way down in some, great-grandchild node and not knowing where you are, not knowing the relationship to the parent node. That might be hard. And if we go back a slide, you can see that this this yellow figure on the left and on the right is indicating where you're at in the tree. Now, it's an important information to indicate, here's where I am in the tree, how deep I am. You can also tell that by color, but the color key shown right here also indicates that much more directly, and how deep you are. So the strengths are, it's good for showing trees with a size attribute, not so good for showing structure. In the tree map and its relatives, all of the pixels are really dedicated for depicting size. In the zoomology thing shown at the end, you're not showing a quantitative value. That's kind of relaxed as a requirement, and so therefore it gets back to being reasonable with showing structure. But for tree maps, where you typically have a fixed amount of space and you're not zooming in and zooming out to any significant degree, then showing structure is not. Tree maps are not necessarily so good for that. It also doesn't overtly depict links other than parent-child, and parent is basically contains children. If you want to show other links, then that's hard to do. And supporting visual search for a single item is also hard. So, for example, when I was talking about Alibaba in 2020, I briefly looked for Alibaba in the 2017 map, and then I stopped because I'm looking for Baba in this field of things with white text on reddish or greenish background. So it's hard to do, and that's just a drawback of the technique. Each technique is going to have its strengths and weaknesses. So that wraps it up for talking about space filling tree drawing and the end of lecture 9.4.